Welcome to Earth Science. Today's topic is the scientific process. So we're going to start off with what is science. Science is a body of knowledge, and it's also a process. It's the process that generates and tests ideas to build new knowledge. But it has some limits. Science is limited to focusing only on the natural world. It doesn't make claims about the supernatural world, and it also doesn't make moral or aesthetic judgments. It can't tell us what's right or wrong, what's good or bad, or what's beautiful or ugly. Science doesn't tell you how to use scientific knowledge. That's something that we have to determine on our own or as a society. We know that scientists are human, they have their own opinions and worldviews, so how can we avoid bias in science? Scientists use objective evidence, that's without personal bias, rather than subjective evidence. That's based on personal feelings and beliefs. So if we were to describe this rock, I could say that azurite, this is azurite, that's a copper-containing mineral. It's blue, it's kind of heavy, and it's also hard. But you'll notice that those might seem different to somebody else. What I just use are qualitative observations that are very general or relative. What's more useful to scientists is to use quantitative measurements that are more objective. So I could say that the rock reflects light at about 450 nanometers, and that's what gives it its blue color. I could put it on this scale, and I could see that it weighs about 118 grams. I could also measure how hard it is on the Mohs hardness scale, and we can see that it's about as hard as a copper penny. So those are quantitative measurements, and they're expressed with specific numerical value. Quantitative measurements allow scientists to analyze data statistically. It helps them to find patterns, it helps them to determine relationships, and they can create mathematical models that help them to explain natural phenomena. Another characteristic of science is that the hypotheses must be falsifiable. A hypothesis is a proposed explanation for an observation that can be tested. If it's falsifiable, then the initial hypothesis may be tested, and evidence could possibly be found that may not be consistent with the hypothesis. This is what determines pseudoscience from science. Pseudoscience is a collection of ideas that appear scientific. They may even use quantitative measurements, but they're not falsifiable, and they don't use the scientific method. Some examples of pseudoscience include astrology, cryptozoology like the study of Bigfoot or the Loch Ness Monster, or paranormal or metaphysical claims. So I'm sure you've learned about the scientific method. That includes asking a question, formulating a hypothesis, perform an experiment, collect and analyze data, and draw conclusions, right? And then you have your conclusion. But actually, that's too simple. Scientists use a cyclical process that you can enter or exit at any moment, and it's much more of a process than a step-by-step recipe. As you can see in this image, science has different phases, and it's more of a process where they can be engaged in exploration and discovery, or the heart of science, which is really testing ideas. They use community analysis and feedback. Science is a social process. And then also, we get involved as a general public in benefits and outcomes from science. So let's take a more close look at each of these phases. During the exploration and discovery phase, scientists are coming up with their questions. Maybe new technologies are giving them new ideas, or they're personally motivated, or they find a surprising observation, or they're just curious about something. So they're asking questions, sharing data and ideas, and of course exploring the literature, because it's important to know what past scientists have discovered and also what your colleagues around the world are working on. The heart of science is really testing those ideas. So here you're putting forth your hypotheses, you've designed experiments in order to answer those questions, and then you collect data to see if that supports your hypothesis or if it opposes a hypothesis. This might inspire a new hypothesis or to be able to revise it and ask a new question. During the community analysis and feedback phase, you get together with colleagues at conferences and you publish, you get feedback and peer review. And other scientists may engage in replication to see if they get the same results as you did. You discuss with your colleagues, and of course you're involved in publication in scientific journals. This is where you can come up with new questions and new ideas, and together with the scientific community, you build theories. We'll talk more about theories in a minute. During the benefits and outcomes phase, this is where everyone can get involved, where new technologies are being developed, we address societal issues based on scientific knowledge, build knowledge, satisfy our curiosity, and of course, inform policy. Some policy decisions include decisions about climate change, or healthcare, or education, or the use of technology for defense, such as the Manhattan Project, or even the space program. So as you can see, this is not a linear process that scientists go through. It's a very engaging and social process. So let's talk more about theory, because it may not be what you think. In general, everyday life, we use the word theory differently than scientists use the word theory. In science, a theory is not just guesswork or speculation. It is a well-substantiated explanation of some aspect of the natural world. It can incorporate facts, laws, inferences, and tested hypotheses. A theory must be testable. It has to lead to new areas of research. A theory allows scientists to make predictions. It is strongly supported by multiple lines of evidence, and it can be strengthened and even revised based on more evidence. An example of a theory in this class will be the theory of plate tectonics, which took decades and many scientists to agree upon a theory. So I hope you've learned more about science, the scientific process, and how scientists do their work, and even how you're engaged in the scientific process. I'll see you next time.